Scientists looking for life on other planets like to talk about the Goldilocks zone, and now NASA's found a...
I'm sure you've heard the news about supernovae, but do you know just how crucial they are to the cosmos? Stars are the cosmic engines that light up our universe. They are the beacons of light that have guided humanity for millennia, serving as both navigational aids and sources of wonder. From the ancient civilizations that charted their movements to modern astronomers who study their intricate details, stars have always been a focal point of human curiosity. They are born from clouds of gas and dust ignited by the fusion of hydrogen into helium deep within their cores. This process, known as nuclear fusion, is what gives stars their incredible energy and luminosity. In these stellar nurseries, gravity pulls the gas and dust together, creating dense regions where new stars are born. For millions or even billions of years, stars shine brightly, fueled by this nuclear furnace. During this time, they undergo various stages of evolution, each marked by changes in their size, temperature, and brightness. Some stars, like our Sun, have relatively stable lifespans, while others experience more dramatic changes. But even stars have a lifespan. They are not eternal. Their lives are finite and governed by the laws of physics. The life cycle of a star is a complex interplay of forces, including gravity, pressure, and nuclear reactions. Understanding this life cycle helps us comprehend the broader workings of the universe. Massive stars, much larger than our own Sun, live fast and die young. These colossal stars, often tens or even hundreds of times more massive than the Sun, burn through their fuel at an extraordinary rate. Their immense size and energy output make them some of the most fascinating objects in the cosmos. They burn through their fuel reserves at an extraordinary rate. As they consume their hydrogen fuel, they produce heavier elements like helium, carbon, and oxygen. This process continues until they reach a point where they can no longer sustain nuclear fusion in their cores. As their fuel dwindles, these stellar giants reach a critical point. They expand into red supergiants, their outer layers swelling to many times their original size. This phase is a prelude to the dramatic events that will soon unfold. They can no longer support their own immense weight. The balance between the outward pressure from nuclear fusion and the inward pull of gravity is disrupted. Gravity takes over, causing the star's core to collapse in on itself. This triggers a cataclysmic explosion known as a supernova. The energy released in a supernova is so immense that it can outshine an entire galaxy for a brief period. The explosion sends shockwaves through space, affecting everything in its vicinity. Supernovae are some of the most energetic events in the universe. They are not just spectacular light shows, they play a crucial role in the cosmic ecosystem. The energy and matter released in a supernova can trigger the formation of new stars and planets. They briefly outshine entire galaxies. This temporary brilliance is a testament to the incredible power of these explosions. For a short time, a single supernova can be more luminous than all the stars in its host galaxy combined. These explosions release vast amounts of energy and matter into space, including the heavy elements forged in the star's core. Elements like carbon, oxygen, and iron are scattered across the cosmos, seeding the formation of new celestial bodies. These elements, like carbon, oxygen, and iron, are the building blocks of planets and life itself. Without supernovae, the universe would lack the diversity of elements needed to form complex structures, including living organisms. Supernovae are essential for enriching galaxies with these heavy elements, seeding the formation of new stars and planetary systems. The remnants of these explosions mix with interstellar gas and dust, creating fertile grounds for new star formation. They are a crucial part of the cosmic cycle of stellar birth, life, and death. This cycle ensures the continuous renewal of the universe, with old stars giving way to new ones in an endless dance of creation and destruction. For decades, astronomers have studied supernovae, unraveling the mysteries of these celestial fireworks. Their research has provided invaluable insights into the processes that govern the life and death of stars. These powerful explosions have provided valuable insights into the life cycle of stars and the evolution of galaxies. By studying supernovae, scientists can learn about the conditions that lead to star formation and the factors that influence galaxy development. However, recent observations have challenged our understanding of how massive stars die. New data suggests that not all massive stars end their lives in a blaze of glory. Some may undergo a different, less dramatic fate. Some stars, it seems, depart the cosmic stage with barely a whisper, not a bang. These so-called failed supernovae collapsed directly into black holes without the explosive finale. This discovery has opened new avenues of research, prompting scientists to rethink their models of stellar death. In the nearby Andromeda galaxy, a massive star much larger than our Sun vanished without a trace. This star, known as M31 2014 DDS1, had been a subject of great interest for astronomers for many years. Astronomers had been monitoring this star, known as M31 2014 DDS1, for years, expecting it to end its life in a brilliant supernova. They had their telescopes trained on it, ready to capture every moment of what they believed would be a spectacular cosmic event. They were ready to capture this celestial spectacle in unprecedented detail. The anticipation was palpable, as scientists prepared their instruments and set up observation schedules to ensure they wouldn't miss a single second of the expected explosion. However, when the time came, the star simply disappeared. There was no grand finale, no explosion lighting up the galaxy. Instead, the star just faded away, leaving behind an empty spot in the sky where it once shone brightly. There was no explosion, no blinding flash of light. The star's disappearance was so sudden and so complete that it left astronomers in a state of shock and confusion. It was as if the star had simply blinked out of existence. One moment it was there, a massive burning ball of gas, and the next, it was gone, leaving no trace behind. This unexpected disappearance left astronomers baffled. They had never seen anything like it before, and it challenged their understanding of how stars live and die. Where did the star go? What could cause a massive star to vanish without a supernova? These questions haunted the scientific community, prompting a flurry of research and speculation. What could cause a massive star to vanish without a supernova? Some scientists speculated that the star might have collapsed directly into a black hole, bypassing the supernova stage entirely. The case of M31 2014 DDS1 challenged the long-held assumption that all massive stars end their lives in spectacular explosions. It suggested that there might be other less dramatic ways for stars to die. It hinted at a more subtle, less understood process at play. Perhaps there are mechanisms at work in the universe that we have yet to discover, processes that can cause a star to disappear without a trace. This discovery forced scientists to reconsider their models of stellar evolution. They had to go back to the drawing board, re-evaluating their theories and looking for new explanations for the mysterious disappearance. Could there be other ways for massive stars to die, ways that had gone unnoticed until now? The disappearance of M31 2014 DDS1 opened up a whole new field of inquiry, as scientists began to explore the possibility of failed supernova and other unknown phenomena. The vanishing star in Andromeda was not an isolated incident. Similar cases of disappearing stars have been observed in other galaxies, suggesting that this might be a more common occurrence than previously thought. Similar cases of disappearing stars have been observed in other galaxies. These observations have led scientists to believe that failed supernovae might be more common than we ever imagined. These observations suggest that failed supernovae, as they are now known, might be more common than previously thought. This realization has profound implications for our understanding of the universe and the objects that populate it. This realization has profound implications for our understanding of the universe and the objects that populate it. It challenges our current models and forces us to rethink what we know about the life and death of stars. The mystery of M31 2014 DDS1 continues to intrigue and inspire astronomers, driving them to explore the unknown and uncover the secrets of the cosmos. A failed supernova occurs when a massive star collapses under its own gravity but fails to produce a visible explosion. This phenomenon is both fascinating and perplexing to astronomers and astrophysicists alike. Unlike the dramatic and visually stunning supernovae that light up the cosmos, a failed supernova is a silent event, almost like a whisper in the vast expanse of space. Instead of a brilliant outburst, the star implodes silently, leaving behind a black hole. This quiet collapse is a stark contrast to the explosive deaths of other stars, which can outshine entire galaxies for a brief period. The black hole left behind is a remnant of the star's core, a dense and mysterious object that continues to intrigue scientists. This seemingly counterintuitive phenomenon can be explained by the extreme conditions found within the core of a dying star. The core, which is the heart of the star, undergoes dramatic changes as the star reaches the end of its life. The intense pressure and temperature within the core play a crucial role in the star's final moments. As the core collapses, it becomes incredibly dense and hot. The density and temperature reach levels that are almost unimaginable, creating an environment where normal atomic structures cannot survive. The core's collapse is a rapid and violent process, driven by the relentless force of gravity. The atoms themselves are crushed, and the core transforms into a sea of subatomic particles. This transformation is a fundamental change in the nature of matter, as the familiar building blocks of atoms are broken down into their most basic components. The core becomes a chaotic mix of particles, a state that is far removed from the orderly structure of a living star. Under these extreme conditions, a strange quantum mechanical effect comes into play. Quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales, governs the interactions within the collapsing core. These effects are not only fascinating but also crucial to understanding the final fate of the star. Protons and electrons, the building blocks of atoms, are forced together, converting them into neutrons. This process, known as neutronization, is a key step in the transformation of the core. Neutronization changes the core's composition and properties, setting the stage for the formation of a black hole. This process, known as neutronization, releases a tremendous amount of energy, but this energy is trapped within the collapsing core. The energy, which would normally power a supernova explosion, is unable to escape the dense core. Instead, it contributes to the core's further collapse. It cannot escape to power a visible explosion. The trapped energy accelerates the collapse, driving the core to even greater densities. This lack of an outward explosion is what makes a failed supernova so different from its more dramatic counterparts. Instead, the energy further accelerates the collapse, leading to the formation of a black hole. The black hole is the final stage in the life of the star, a point where gravity has become so strong that not even light can escape. The formation of a black hole is a profound event, marking the end of the star's journey and the beginning of a new enigmatic object. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. This intense gravitational pull creates a boundary known as the event horizon, beyond which nothing can return. The black hole's gravity warps space-time itself, creating a region of the universe that is fundamentally different from anything else. It is the ultimate cosmic sink, a point of infinite density and zero volume. The black hole's core, or singularity, is a place where the laws of physics as we know them break down. This singularity is a mystery that continues to challenge our understanding of the universe. The concept of a failed supernova challenges our understanding of black hole formation. It suggests that there are multiple pathways to the creation of these enigmatic objects. This new understanding forces us to rethink our models of stellar evolution and the life cycles of stars. Previously, it was thought that black holes primarily formed from the remnants of supernova explosions. These explosive events were believed to be the main way that black holes were created, with the core of the star collapsing into a black hole after the outer layers were blown away. However, failed supernovae suggest that black holes can also form directly from the collapse of massive stars. This direct collapse bypasses the explosive phase, leading to a quieter but equally dramatic end for the star. This alternative pathway adds a new dimension to our understanding of black hole formation. This alternative pathway to black hole formation could have significant implications for the evolution of galaxies and the distribution of black holes throughout the universe. Understanding failed supernovae helps us to better grasp the complex processes that shape the cosmos. It also opens up new questions about the life and death of stars, the nature of black holes, and the ultimate fate of the universe itself.